Okay, good. Microphone, there we go. And I don't know if this works. Good, thank you. Well, great to see everyone, and here I am talking about what I hinted to yesterday of why plasma lensing is actually a good thing. In fact, the most interesting thing about FRBs in general, right? That's why I think I dropped everything I was doing in cosmology and thought FRBs are clearly the most important thing that dragged others along. Kyo at the time was doing cosmology, and we all got diverted by FRBs along the way. Let me just explain why I feel FRBs are special. I mean, obviously they're special in many ways, but there's one metric where they're special by 20 orders of magnitude over any other measurement in the universe, and I think this is something which is not being thought about much and has potential. So I'm going to try to explain the basic opportunities here. FRBs are coherent, they scintillate. And just for reference, pulsars in our galaxies are known to scintillate, and there's to first approximation, no extragalactic source that scintillates. I mean, if you want to be nitpicky, some people might say there have been scintillation observed in GMB afterwards, but it's unrelated, really. Okay, this is the only truly scintillating object, meaning they are point-like under propagation. Wave effects matter, and you can measure things to a wavelength, which is centimeters for FRBs. You're measuring something to incredibly high precision. And you have to start thinking, how do you even calculate how to predict these things? Can we understand them? And can we use this potential very high precision wave optics phenomenon? And I'm going to speculate a bit about other related phenomena. There's another class of objects that is also coherent wave optics, which are gravitational waves. So now we have two probes that are extragalactic distances that are point-like and have wave effects. I mentioned this strain. So if you're saying you're measuring a nanosecond time delay over gigaparsecs, so the delta L over L is, it just takes us to numbers, about 10 to the minus 26. Okay, this is orders of magnitude more precise than the LIGO measurements of 2 arm lengths. It's, that's by far the most precise number that you could think about measuring. The question is, how do you translate this, in principle, very, very sensitive probe into observables that we might want to understand? So here we come along. This is Kyo's, I think, first distraction from what he was doing in cosmology at the time, was analyzing GBT data to find the dark intensity mapping 21 centimeter for dark energy purposes. And Shoshen and Kyo found an FRB in the 21 centimeter data. It was at a time that people started realizing that 21 centimeter cosmology is not, there's life after cosmology. And we started diverting the CHIME effort to also start looking at FRBs, since these are clearly the same. You want almost the same specs. You want a lot of sensitivity, a lot of sky area, and a compact aperture. So you got, for different reasons, but it turns out to be the same prescription. And again, it's actually these. This is the first real report of scintillation in an FRB. In hindsight, if you look at the earlier data, it looks like they were scintillating too. But this is, to my knowledge, at least the first paper where this was explicitly described, and the scintillation bandwidth was measured in a FRB. And that opens the door to try to do coherent measurements to a wavelength out to very far distances. To step back a little bit and say, well, do we know that any of this works? Here's an example of astrometry with a pulsar. And in fact, I know many of you have been engaged in this thing over the years. I'm even wearing a scintillometry t-shirt today, so unlike yesterday where Inge was complaining that I was just on vacation, now I'm professional, see, I'm wearing a scintillometry t-shirt. And Inge is no longer dressed as a bodyguard, so now we blend right in. So here, this Adam was involved in this data and in the paper, where we use a interstellar telescope. It's a screen in the Milky Way. Here's what it looks like on the sky, on combination of VLBI and scintillation reconstruction. So here's a pulsar as it moves. Here's the images of the pulsar through plasma lensing as the pulsar moves. Of course, this particular pulsar, 0834 plus 07, doesn't say so. Obviously, it's got two things: it has a proper motion, and then this wiggle is the Earth-Sun orbit. So this reflection of that. With VLBI, you measure the geometry on the sky and the time delay. With an angle and a time delay, you measure a distance. So the distance to this screen is 389 parsecs. The distance to this upper screen is just over 400 parsecs. It's at a slightly different distance. All these things are measured to 3 or 4 significant digits, let's say 3. So this is a highly precise measurement of distances. Okay. Now, there are complications of what you have. You measure a combination, of course, of screen and pulsar distance. And this combination, I haven't quoted the pulsar uncertainty. The pulsar, of course, Adam has measured directly with VLBI astrometry independently. But for this purpose, what matters is that there is a screen of known geometry and known distance that you can use as a telescope. This is multi-billions of kilometers in baseline length. And it's got 2 axes. You've got one axis along here, and it's even changing with time. You've got another little image off to the side. And you can use that to image the emission point of the pulsar as it rotates over pulsar rotational phase, measured in milliseconds. And you can see that you're sensitive to, and because we know all the geometry, we can measure in kilometers the motion of the emission point on the sky by the pulsar with an uncertainty of a few kilometers. Okay? So this gives you a direct application of how you can measure things to picoarc seconds. Normally that's 50 picoarc seconds as an object rotates with good control of your lensing optics. So here's an example of how you combine interstellar lensing to make a coherent, truly big telescope, billions of kilometers in baseline length. Just for reference, this is almost 1 million times higher resolution than the EHT black hole images. Okay, this one circles around any kind of imaging astrometric precision that we normally hear about, and that make much more news. So even I think this is obvious. In fact, I'm going to jump ahead to the result that this has been used by Calvin and others to search for black holes, to search for compact dark matter, which by microlens. If you get microlenses can be caused by potentially compact dark matter if it were compact, but stars will microlens, and that's not negotiable. And in fact, that optical depth is not that tiny. It's basically omega in stars. So 1 in 1,000 or so FRBs should be lensed by just a random star somewhere in the universe. So these things should have already happened. We just need to think of how to search for them efficiently. And with such microlensing, you can ask, can we again just get cosmological distances out directly? Well, just a quick summary again. This is Calvin's paper on using this to constrain dark matter. And if they were compact point sources, you can ask him directly how that works. I'm going to just explain a cosmological, a more direct application of what you would do with a stellar lens FRB. So the things that you measure, if you have a micro-lensed FRB, is you measure a voltage stream and a delayed voltage stream by a few microseconds in the case of the star. So you can measure the time delay by just looking for the correlations in the voltages if you have baseband. And you require to know, you also know the flux ratio, that's directly, to see how much flux there is in each of these in the image. You measure the delay, the flux ratio, and then you've got to do some homework. It measures the redshift of the source and the lens galaxy, which is where the microlens is. And to get an absolute distance, so you have the angle, and then you need a time, you need a time delay, you still need an angle to get a distance. These angles are, again, micro-arcseconds, so you might think they're a bit small for on-based VLBI. But luckily, we have these plasma screens that are fairly ubiquitous along the lines of sight of our galaxy. So we can use VLBI, to, just like in OH34, to image the lensing geometry of the screens and use that as a telescope to measure the splitting angle of the microlens images. Okay. That is the approach here. And so the good news is that many of the upcoming localizations like CHIME will have continental-sized baselines that are perfectly suited to measure these scattering geometries of FRBs. So this is well on its way to being explored. And so as we said, these are two lenses. This is my student Anna and company. So working this out we have various distances, you've got a micro lens, and then you have a ISM plasma lens now in a Milky Way that gives you this added boost of angular resolution. And this is the idea of the application of using it. I obviously think the really interesting part of it is the theoretical implications of how to compute any of these things. We've had a lot of fun computing how to do wave optics efficiently and intuitively, and it turns out there's something called Picard-Lefschetz theory, that what you have to do is solve not just for the real images using Snell's laws, geometric optics, but also for the complex solutions of Snell's law. And with those combined, it turns out you can even measure lensing time delays when you have weak lensing. Okay, even though you may not have enough lensing depth to have extra images, the wave optics explores multiple paths for you anyway, so you can have a chance of getting lensing time delays even when you don't have a real second image. And jump ahead, I think this is more detail than I was scheduled time for. And the same applies for gravitational waves, that one can do fun optics of lensed PTA gravitational waves, that it turns out it's a completely different regime. Everything you've learned about geometric optics, because PTA, like at light years wavelengths, the geometric optics is almost irrelevant. Everything you might estimate there is off by orders of magnitude, and your wave optics turns out it's the galaxies that are many arc minutes away from your line of sight dominate the wave optics lensing, scattering cross-section. So just have to go back, forget about everything you learned about lensing, and do it again, and you find out, oh, there's actually a lot of interesting things that we measure that we normally don't think. We have to re-educate ourselves to think about just how waves propagate in an inhomogeneous medium. It's not profoundly new, but it's actually very helpful in cosmology. So just a quick summary that I think there's a lot of promise of using the coherency of FRBs to map all kinds of things about the universe itself, and of course about the lenses. I could go on forever about speculation of why those lensed images look so strange. Why is the lens along a straight line, primarily, with a little island off to the side? Okay, don't mention this word extreme scattering events. There are all kinds of interesting things that this allows us to probe that could be interesting on its own. So I think this is a very fruitful set of observables that I'm encouraging everyone to start thinking more about. Thank you.
Thanks, Ue-Li. Are there any questions for Ue-Li?
Hi, very impressive talk. Can you go back to the slide that you made, people asking and you made the pulsars? You mentioned at some point that you're doing VLBI for this, right? And then you also measure the time delay. My question is, did you do this at the same time? Like you're doing VLBI and then you use the same station to measure, basically use VLBI and you're observing with VLBI and pulsar mode at the same time, or did you doing that separately?
Well, it's the same data, and in fact, Adam Della was directly involved in that analysis. But because you have basically measuring the electric field at two stations, from the order correlation of the electric field, you measure the time delay, and then from the comparison of different stations, you measure the angle between them. It's a bit technical, but it's the information is basically in using so basically the same as in the microlensing. You search the voltages for time delay within, and then you see phase lag across telescopes.
Right.
Same data.
That's really clear for me.
Yeah, thanks for the talk. I was curious, is there a limitation to the amount of magnification you can get from a binary supermassive black hole?
Magnification, you mean of the gravitational wave?
Of the gravitational wave, so yeah.
Binary supermassive black hole. Yeah, the short of it is that the Fresnel scale of that is kiloparsecs, meaning you never get any useful magnification from of those by lenses. Lenses don't, they're always in the weak diffractive regime. But if you have enough signal to noise, you can actually see all the diffracted images, and the kind of program there would be to measure, again, both angles and time delays, and measure direct distances to these supermassive black holes.
Thanks. Are there any? We can have one more question while Ines setting up.
Just not sure I quite understand the method for using the lensing of the FRB. Do you need, it doesn't need to be a repeater. You can just do it off a single burst?
Yes, but of course you have to have VLBI at the time you took it. Like now, of course, almost all VLBI data is on repeaters. Okay. Repeaters get microlens too, so but you have to have more. You have to watch more often.
Okay, thanks, Ue-Li again. Now we have Ines talking about